Okay, so that's the bit about variables. So we're going to look at now about setting up a servo loop. So I don't know how familiar you are all with servo control. I know probably Mark's got a little bit of background there. But in one of our controllers, what we're tending to do is that we do the intelligent sort of positioning bit and the motion profiling bit, and we leave it to the servo drive to do the control of the motor, if you like. So we're not really involved in controlling a stepper motor or controlling a servo motor as such. We leave the drive to do that. And you mentioned hydraulic systems, Mark. We would assume somewhere there's a hydraulic controller somewhere that's controlling the current into the hydraulic valve. Although a lot of modern valves and motors actually have an electronic package on the back, which kind of does that. So in some cases, this drive package might be actually bolted on the back of the motor. So what we're giving out is a speed reference plus or minus 10 volts, and we're getting a position feedback as usually an encoder simulation. So there is either an encoder or a resolver on the back of the motor which is feeding into the servo drive, and that's doing the control of the speed loop and commutating the motor. And then it gives us encoder pulses to tell us what the motor position is. So inside the controller, we want to be controlling the position of the motor, so we have to take that feedback information and compare it with our required position, which is over on the left hand side there, and then output a voltage to tell the motor which way to go, because that voltage is proportional to speed. So here we've got a voltage where 5 volts would give you 50% full speed. So if it's a 3000 RPM motor, 10 volts is 3000 RPM, and things should be linear. We hope it is anyway. The feedback coming in could be an incremental encoder or an absolute encoder, and that becomes what we call the measured position inside. Gets compared with that and then goes through a typical PID control loop. If I stick some numbers in and give you an indication now of the sort of names we use. So we call the measured position MPOS. That's measured position. We call the demanded position DPOS, and the two, when they're compared, becomes the following error, which we call FE. So these are all quite cryptic, but the reason they're cryptic is because these names originate from the 1980s when the controllers were first developed. So in those days, microprocessors weren't so powerful, and so names were generally kept quite short to save memory and stuff. So on the picture I've got there, we've got a required position of 2000. Now why have I chosen numbers like that? Okay, I should just explain that the wheels you've got on there, they have encoders on which give 4000 counts per turn. So if we don't set anything to calibrate that, we're just dealing in encoder counts. So one turn of that motor is 4000. So what I'm saying there, with a DPOS of 2000, the thing should be down at half a turn. And what we're saying as well is the actual position counted in from the encoder pulses is only 1999, so there's a 1 count difference. So that 1 count difference goes into the PID bit here, and all I've done is set a P gain of 2, and that literally is just a multiplier. It's just mathematically a multiplier. So it multiplies the following error by 2, we get a value of 2 here. On the 12-bit D2A converter, that gives us that voltage, 0.0048. Okay, and that usually is enough to push the motor into position. With modern systems, it's quite unusual for that not to actually achieve it. You think, well, 1 count difference is ever so small, but most modern servo motors will correct that. The time it won't do it, for example, is if you've got the motor's got some weight on it. So if it is a winch and it's pulling something up and there's some mass there, that will be pulling it down, and you'll get an offset because of gravity, basically. So there are conditions where it won't actually pull in. Now that's a brilliant system. We can set the P gain to some value. We're going to talk about what sort of values to put in it in a minute. And you might think that if I just increase that P gain, if I made that 20, for example, I'd get a value of 20 here, and then I'd have a bigger voltage and it would pull into position even faster. But there is a problem with that, because then it starts to overshoot and you get oscillations occurring. So there's only so much you can do with the P gain. And one of the issues with P gain is in systems where you actually want one axis to follow another, or you want to follow a track very accurately, is that you end up with following errors when you're moving. And the reason for that is, this is only a multiplier, and if I want to move this motor, if I want to move that motor, say a quarter full speed, I need some voltage out of here. I need 2.5 volts. So again, if it's a 3000 RPM motor and I want to go at 750 RPM, I need to output 2.5 volts there to make it move, otherwise it ain't going to move. And in order to make that have 2.5 volts there, I need a value here of 512, because that's a quarter of 12-bit signed value. 2047 is the 10 volt value, 512 is the 2.5 volt value. And in order to have that here, I have to have it coming out of my P gain. In order for that to happen, I have to have a following error. The whole thing just, logically works backwards. So when I'm moving, this is a snapshot, okay? So DPOS is 3000 now, but in a second it's going to be a different value. It's actually moving, but this is just a snapshot. I do have this following error, so the faster I go, the bigger the following error will be. So in a P gain only system, you will get lags all the time. When you accelerate and decelerate, the actual position will follow behind what my required position is. And if I'm trying to make lots of axes all follow one another, then that's going to be quite arbitrary. It's going to be quite difficult to control. So we want some way of, of getting that following error down as low as possible while we're moving. And that's where the I and the D come in. Because what an integrator does, it says, what's that following error? Okay, if I have an I gain set in here of some value, it will multiply the following error by the I gain and output it there, but it will keep it. And then in the next servo cycle, it says, what's the following error now? And it adds it, so it keeps on adding it to a total, until eventually, over sort of quite a few hundred milliseconds, it will actually have the output needed to keep it going at that speed. So that's what we have here. So we've set an I gain here. It's quite small. So over a series of servo cycles, it will have said following error times 0.01 gives me an output. So first time round, remember my following error there's 2.56. So first time round, the output of this is going to be 2.56. And the next servo cycle, it's going to be 5.12. The next servo cycle is going to add it again. But all the time it's adding that, it will actually be reducing the following error, because the output of the D to A converter to give you the speed is now coming from the I gain output, not the P gain. So the higher that gets, the less the P gain has to be, because the total here has to be the same all the time. So basically just increments up until eventually you've got the I gain giving you all of the speed you want, and then you've got no following error, which is brilliant, except that it did take a few hundred milliseconds to do that, and then if I stop suddenly, it's going to take a few hundred milliseconds to ramp down again, so you get overshoots when you're using I gain. Now you can dampen out the overshoots by using D gain. So if I shove in some D gain here, what that does, it says, right, if there's any sudden change in following error, I'm going to output that into the signal here to basically put the brakes on. So if I get a sudden change in following error as we want to decelerate, that will output a kind of a big braking action, in other words a negative value, to overcome the I gain. So you can tune PI and D. It takes quite a bit of care to do it, to make a system that's both got very low following error when moving constantly and responsive when you change speed. But it is quite a tricky thing to do. And although we have the facility to do that, 95% of all systems don't use it. They just use P gain as required to keep things in position, and something called VFF gain. And we can use that because in our software we know what speed we want to do. So if we know what speed we want to do, if we multiply that by some factor, we can actually output the voltage that we want to do that speed even before any P loop is trying to output it. So you're saying, right, this is the speed, that's the voltage for the speed, and this bit here just basically mops up the difference if it gets a little bit out of position. And that's really easy to set up. You can even calculate the VFF gain. It's quite repeatable. Velocity feed forward, yeah. So most systems use that, and I don't really get involved in helping people set up PID loops, because it's a nightmare.
Do we have any auto-tuning functions either in this or in the drive?
Well, the drive will have auto-tuning functions probably, depending on the drive. We don't have any auto-tuning for the P loop. It's not a trivial thing to do, should we say. It's quite complex, because you have to take account of inertias and all sorts of things. And yeah, I mean, I have no idea what the maths is for auto-tuning a P loop. And if it was easy, or even if it was not easy, but quite doable, we would have done it by now. But it is a very tricky thing.
Just to recap very quickly, if you use velocity feed forwards, you don't need IMD.
You don't need IMD.
You just need a arbitrary proportional gain.
Well,
I've never fully appreciated that.
You say arbitrary.
A number that.
Yeah, it should be a reasonably thought out proportional gain.
Right.
Yeah, you don't need the I and the D, because the VFF gain will take care of it. But there is an assumption, though, that this is proportional to speed. If you're dealing with a hydraulic system, it might well be that it's not.
No.
The signal to the valve is going to be proportional to valve opening, which is going to have some proportionality to oil flow.
It's
but
not necessarily linear.
Exactly. So it does depend on there being a linear relationship here. So I used to work in the hydraulics industry, and PID was used a lot there, and very little velocity feed forward.
Right.
But they had other gain factors actually to do with pressure sensing on cylinders as well, which was quite neat. But that's a different. Don't need that with electrics.
Yeah.
What kind of application we can just go for VFF gain steady instead of PI? I mean, do you have any idea?
All of them.
All of them.
Yeah. So the only time I've come across our controller, someone actually using PID, was in a couple of research laboratories where there were some very clever guys who wanted the challenge, and I'm sure they did a better job than you would do with P gain and VFF. But they were very expert. They knew exactly what they were doing. I'm not saying you have to be expert to use PID. You can get quite good results even if you're just by trial and error.
Exactly.
But one of the problems with PID is it is a bit load sensitive. So if you have a load that changes, then effectively the gains have to change as the load changes. So it's okay if the load's constant. Whereas VFF gain is just, it's really repeatable. And P gain on its own can be made a bit less load sensitive as well, because you just reduce it to a fairly low level, and then it still works. So to actually tune a loop, to set up the P loop, the P gain, the sort of standard way to do it, if you like, this is quite old fashioned, I used to use this in hydraulics as well, is just to step the axis backwards and forwards a little bit, by quite a small distance. So in this case, in a motor, say 45 degrees of shaft movement, just go backwards and forwards. And then we look at the actual movement after we've done this, and we try to give that an instantaneous change of position, effectively. It's called a step, so it literally is that. So I don't know if you can see it, the red line there is the step, that's the demanded position, so we're telling it to do the impossible. We're telling it to go 45 degrees in an infinitely fast speed. And then we look at what its actual response is, which is the blue trace on there. And effectively, if it's got too much damping, in other words, the gain's too low, the P gain's too low, then you would have what you can see there, where it's kind of goes up fairly lazily into position with not too much overshoot, and it's taking. There's a little bit of a hump here, so say it's getting to about there in position, isn't it? So that's 1, 2, 3, 4, 5 lines on there, and it's 20 milliseconds ago, so that's 100 milliseconds to get to position. If I increase the P gain, I can get it to position a lot faster than that, so we're getting it in about 2.5 squares. Oh, hang on, it starts there, doesn't it? So it's 0.5, so about 3 times 20, so about 60 milliseconds now we're getting it actually into position. Now there's a little hump there as it goes there, but that's okay because we're giving it a very false movement here. We'll never do that for real. You'll always ramp it up to speed. There'll be a profile that you'll ramp it up to speed. So what we're looking at here is it's not a real world kind of motion. We're just trying to trigger it to see how stable it is. Yeah, we're just trying to trigger the control loop system to look for stability. And if I go up a bit more in terms of gain, which I hope the next one shows us, there we go, we start going into this kind of oscillatory kind of picture. So now we've got probably a bit too much P gain, and it's starting to go unstable. If I put even more P gain in, then eventually you can imagine this will become a constant oscillation, and you'll have a motor that's just buzzing completely. If it's a motor on a big mass, it would actually start to get quite scary, because you've got a large mass flying around doing that. So you need to treat it with care. I was at a customer once where the guy typed in, by mistake, he typed in 1,000 instead of 10, and it was a printing machine, and it was the main line shaft, and the whole thing was going, and it was almost walking across the floor because of all this vibration. His boss came flying out of his office and said, "What are you doing to my machine?" So you've got to be a little bit careful, because the gain values, when you're setting them, it is typing in numbers. There are no kind of nice sliders on it. So anyway, the lesson from this particular slide is there's only so much P gain you can put in, otherwise it starts to go unstable. Hence why we then need other ways of giving us lower following errors, because we can only put so much P gain in. Right, so the little task we're going to give you is to write a program which does this, and you've got some sheets with the programs written on for you. I'd like you to sort of start off by typing the programs in. As we go through, maybe by tomorrow, we maybe just hand the programs out on a memory stick. But to start with, it's a good exercise just to get familiar with using the programming interface and actually write some of these down. But the program you've got in front of you, it'll have a little bit more than this, because it does use the dimension command. It'll have DIN commands to set up these variables first. But the guts of it is more or less the same as this. So we're declaring how many counts per turn we've got on the motor, what the maximum speed is, and how far we're going to step it. So we're going to step it 45 degrees, which is 1/8 of a turn. And then the rest of the program sets up the speed to be effectively the maximum RPM. The accel and decel is set to 1,000 times the speed, because it's a 1 millisecond servo cycle. So if you set that to 1,000, it will go instantaneously to that speed. There'll be no ramp at all. It doesn't ramp up and down, and that's what we want. We want to basically trigger this thing and get it to react. We need to set something called following error limit, because we have this value called FE. It's being monitored all the time. If it exceeds the FE limit, then it will trip out the watchdog, as we call it. So it will turn off the servos if the FE gets too high. So we set that to half a turn, so that if our system does go, if you do type in 1,000 by mistake and it starts to oscillate madly, it will trip that out, because the following error will get too big. And then the last two on that page are the two key commands for getting something moving: servo on, watchdog on. I had a customer last week who had been waiting for a week and a half for us to help, because we were at this trade show. He was getting his drive enabled and everything was ready, and he was trying to do moves, and it wasn't moving. And the guys who were trying to help him out didn't spot this, but when I looked at it, he hadn't turned the servo on. If you don't turn the servo on, it won't move. So he waited a week and a half for me to tell him to turn the servo on. So if you remember that little tip, then it will save you a lot of waiting. And then the actual program that does the stepping is this one here. It's just a while loop. So this is in the basic language. I'm hoping that I don't have to go through the whole basic language. Are you okay with general syntax of it? While loops and repeat loops and if thens.
But the syntax of this program, I'm not.
Yeah, it should be okay. Yeah. So we're just basically, while true means go around forever, so it's going to go around that loop. The trigger command triggers the scope. We'll be using the oscilloscope to look at the traces, so we want that synchronized with what's going on. Trigger command triggers scope, and then the rest of it is just moving forwards, wait half a second, move back, wait half a second, but I've split the half second into 2 bits so that when we trigger it, we've got a little 20 millisecond delay before the scope actually, or the motion actually shows on the scope, so we can see the rising edge better. So that's just to make this wait 20 here is just to make the scope look better when we do it. Now all the stuff above it, that isn't used in the program really, it's just an example of how you can calculate VFF gain. But it's not used actually in this, it's simply there as an example. So it just prints out on channel 5, on terminal 5, what the VFF gain would be if the values here are true. So if you've got those values, 4,000 and 3,000, then they're used within the calculation. Okay, so I've got one other thing that I need to say about these rigs though, is that all this time I've been talking about the fact that the output, the 10 volt output is proportional to speed. With these rigs, the little motors on them don't have a speed control. So the little drive is just giving the motor a current, so effectively controlling the torque on the motor, not the speed on the motor. So in order to make them stable, with this particular test we're doing now, or when we use these rigs, we actually have to set a D gain, and it's nothing to do with PID, it's just the fact that there is no speed loop in the drive, but you've got to set a D gain to make these actually work, and probably 30 is a good value. So before you do anything else, set the D gain to 30, otherwise they'll go unstable because there's no speed loop in the drive. So the D gain here, this differential gain, is acting a bit like a speed control. And it's because, say, there's no speed control drives, they're just torque. And that's the only additional thing.
Could you run them as like a torque feed forward instead? Instead of a speed feed forward?
Yeah, we don't really. The thing is, we have no internal value in the trio that's proportional to torque. We're generating a speed value, but there's nothing proportional to torque, so there's nothing there really to feed forward. And likewise, because they're not speed controlled drives, the velocity feed forward won't work because the output's not proportional to speed.
Yeah.
So it's all because when these little demo rigs were designed, they were just designed to be relatively low cost and with small motors and small drives. So they don't use what we commonly use in industry.